today we will be talking about this thermodynamics of combustion, and with a thought process from Lavoisier, right, who says that I consider nature a vast chemical laboratory in which all kinds of composition and decomposition are formed. Vegetation is the basic instrument the creator uses to set all the nature in motion. This is a very important and profound statement, which our ancestors were very much aware. That is why we were a agriculture based country, and chemical reactions always takes place, and whatever the chemical reaction takes place in nature, those are profound and without any effect. That is a very important point. When we talk about chemical reaction, we will be talking about that. And as we discussed in the last lecture about various like heat of formation, heat of reactions, heat of combustions and other thing, how to calculate. Today what we will do, like we will be looking at just to take an example about that and see how we can use. For example, like determine the standard heat of reaction at 298.15 Kelvin for famous water shift reaction as given below. This is a very important water shift reaction, which is basically 1 mole of carbon dioxide reacting with hydrogen. It is going to the carbon monoxide and water. Of course, keep in mind that all these components are in gaseous phase. Now, question arises whether I can get back carbon monoxide can be reacted with the oxidizer to give me what? Carbon dioxide. Am I right? So, if you look at like nature works in cycle, whether I can use this as a cycle or not. Of course, that is not the with this example, because we are interested to determine the standard heat of reaction at 298.15 Kelvin, and this is quite famous. You must be aware about this reaction, that is water shift reaction. How to go about it? I do not know this heat of reaction of this of this particular reaction, then what I will have to do? But however, I will be knowing several other reactions, right. If I know those reactions, can I really get these reactions heat of reaction? That means, heat of reaction of this water shift reaction can I get? And now, let us look at how we can get, that is the following heat of reactions at 291 known, like for example, like CO2 is going to the C plus O2, right. We know that, right, and we also similarly know C plus half O2 going to the CO, right. The carbon is reacting with oxygen going to the CO, and we know that hydrogen reacting with oxygen, half oxygen and going to the water. If I know these 3 reactions, if you add all these things, can I get this water shift reaction? Yes or no, right. If you look at, I can cancel this out, and this oxygen like about this half and half, this I can cancel. What I land it CO2 plus hydrogen is going to the CO plus water, right. But I must know this like heat of reaction. Heat of reaction for this CO2 and plus C plus O2 is basically 393.51 kilojoule. Of course, that is at 298.15 Kelvin, right. If I similarly, I know this reaction, and keep in mind that the earlier reaction was positive and this is negative. That means, the earlier reaction was endothermic and this is exothermic reaction, right. And similarly, the heat of reaction for the third reaction, that is hydrogen plus oxygen going to water, is again an exothermic reaction. So, if I just add this together, as I told you earlier, that what I will get? I will get CO2 plus hydrogen going to the product CO and water, and if I add together, I will get this total heat of reaction for this reaction is equal to 41.16 kilojoule. Just I will add all these three together. But what is the basis for it? From where? How can we do that? Is it right or wrong? Can anybody tell me? Huh? That is basically known as Hess law, which states that resultant heat evolved or absorbed at constant pressure or a constant volume, right, for a given chemical reaction is same whether it takes place in one or many steps. By the way, this Hess law comes from where? Stems from which law? But this is not really the actual law, but people call it. Okay. It has come from your first law of thermodynamics, right, and this is a beautiful concept which is being known as a Hess law, which is just extension of the first law of thermodynamics. Whatever the path it takes, as long as it is having two end points, then it will be dependent on the end point. That means, it is independent of path taken by the reactions. So, that is the basis of the first law of thermodynamics. If you remember, like we are talking about internal energy is a property of the system. So, and this is the one. Now, what we will do? We have now worked with this heat of formation, heat of reaction, then like how to get a heat of reaction by knowing the elementary reaction like CO plus RO, O2, CO kind of things, right. Now, why you will do all these things? What for we will do? Of course, you can say that I need to calculate or estimate the heat of combustion. That is why I need this information. Keep in mind that these heat of formations data are available in the table, tabular form, like Janov table. Of course, in my book Fundamental of Combustion, it is given on the back side in the appendix. You can use those data. Now, question is there apart from estimating the heat of reaction or the heat of combustion, whether we can use those data for something else? Can anybody tell me how we can use those data, which is essential when we talk about combustion? See, we need to find out what will be the maximum temperature one we can think of, right. That is, we call it as a adiabatic flame temperature. That is, the final temperature attained by the burner under adiabatic condition is known as adiabatic flame temperature, right. It can be a burner, like for example, we have taken a burner in which 1 kilomole of methane is entering into the burner, where it is reacting with 2 kilomoles of oxidizer. Of course, all these reactant, that is methane and oxygen, are at 25 degrees Celsius and 0.1 megapascals, right. Okay. Now, if you look at that, it is going to a product, the CO2 and water, right, and what will be the temperature here at the product? Of course, it may be at the pressure of 0.1 megapascal, and keep in mind that if I take this as my burner, this is my burner, right. What will be it is? It is basically I can take this as a control volume. This is my control volume, and no heat is going out of this burner, right. And what are the assumption we need to make? We will have to say that it is the steady process, change in kinetic energy and change in potential energy is 0, right, and no work interactions is taking place, right, and there is no heat interaction as well, right, and it is a flow open system, because some fuel and oxidizer is coming, getting burned and is going out. But there might be a situation where the flow will not be taking place. Okay. Are you getting point? So, then how to handle that you need to worry about, but we are now considering about a flow process or in a burner, right. So, if I will apply this first law of thermodynamics for determining the adiabatic temperature, Do you think it will be sufficient, or you need to know something more about it? Is it sufficient? It will be sufficient provided if we know that product is CO2 and water. Okay. But in real situation it need not to be. For the simplicity sake, we are considering the product to be carbon dioxide and water. Okay. For the time being, let us do that when we apply this first law of thermodynamics under the condition of assumption I have stated just now. For a control volume or a open system, that is H p is equal to H r, right. And this what you will temperature you will get is basically T adiabatic, right. This is the T adiabatic will be because the no heat is going out of the system. So, all the heat will be there. So, whatever temperature I will get, I call it as adiabatic temperature. So, therefore, the product will be dependent on adiabatic, it will be function of adiabatic temperature and pressure. Of course, pressure I am assuming it to be same as that of inlet. Can I assume that pressure, or it will be changing? Will it be changing, or it will be remaining constant? What will happen? The pressure will be remaining almost constant, right, because this is a constant pressure process we are assuming. Okay. And what about heat of reaction? Heat of reaction is basically NiHi, and Ni is the number of moles, right, participating reactant. In this case, it is a methane and oxidizer, whereas Hi is the heat of formation of individual species. And keep in mind that this heat of formation for individual species will be having what you call the heat of the enthalpy of individual species will be having two component. One is this is heat of formation at standard state, right, and this portion is known as sensible enthalpy, we have studied in the last lecture. And this is integrated is a T naught to T particular temperature, right, because the T naught at which all the data will be given, all the heat of formation data will be given, and Cp keep in mind is a function of temperature, right. I cannot take out because temperature will be very high. For example, if the inlet temperature is 298 Kelvin, what will be the adiabatic temperature? What will be the order? In case of a methane oxidizer, it will be very high, it will be around maybe 3000 Kelvin, right. If it is air, it will be lower, right, because nitrogen is there, which is an inert gas. So, therefore, we cannot really assume that Cp is not a function of temperature, rather it is constant. We cannot afford to do that in this case, what we had done earlier while handling the compressible flow. So, similarly, the total enthalpy of the product is summation of Ni and Hi. Hi is the enthalpy of individual species, and it is having two what you call term here. One is heat of formation of the species product, and of course, the sensible enthalpy. Keep in mind that this is being integrated from T naught, that is the inlet temperature, that is the what you call the standard temperature T naught to T adiabatic, right. Okay. So, what we will do, we will just substitute this in this equation, if I look at this equation 1, right. If I say this is the equation 1, if I will substitute Hr and Hp in this equation 1, I will get an expression, right. And then let us look at 298, what do we call? This is basically heat of reaction, right. Heat of reaction Hr, we know that by definition NiHFi with respect to standard condition, and similarly for the reactant, that is NiHFi with respect to standard condition. This is our heat of reaction. If I substitute, look at this equation 1 and substitute those values, we will get the sensible enthalpy. This is change in sensible enthalpy is equal to basically Ni for the product, and Ni I can take, and Cp I T dt. And similarly, for the reactant, Ni Cp dt integrated over T naught to T u, and T u to T adiabatic, because that is the inlet temperature what would be, and which is equal to what, and this is the heat of reaction, this portion, that is the heat of reaction. That means, this data I can get from what, like if you look at this data as heat of formation from table, right, I can get, provided I know what is Ni, that means each stoichiometric or the number of moles, if you look at, I must know, right, for individual species, then only I can get. But do we really know that? In real situation, we do not really know, and those things will be dependent on temperature. For the simplicity sake, I am again repeating, that is, we will be assuming the product to be carbon dioxide and water or something else, but it must be known for the time being, we are assuming. So, when you do that, then we can find out what will be T adiabatic, provided we know that how this Cp is varying. Cp is basically not only dependent on the species, this is the species, that is ith species, it can be methane, it can be oxygen, it can be carbon dioxide, it can be water, anything. It will be dependent on the temperature, like these are coefficients, coefficients, which are to be obtained from the table for a particular species, right, and these are of course a polynomial which being fit. And you will see that from Jenner table, this will be valid for certain range, these coefficients, another set of coefficient will be used for the higher temperature, that you will see. Now, let us just to say that it is let us see that how the Cp is varying with temperature. Let us look at a plot. If you look at Cp for the species like hydrogen, oxygen, water, carbon dioxide is varying with temperature. Of course, for a monoatomic molecule it does not vary, and we do not use this species particularly for our combustion reaction. However, we use CO2, water, oxygen, hydrogen, methane, propane, all those things, and several other species. So, we cannot afford to say that it is remaining constant whenever we are talking about combustion problem, particularly where the temperature will be quite high or the change in temperature will be quite high. So, you should keep in mind this thing. Now, what is the meaning of this? What really we are doing? If you look at, that is, the reactant is going to the product for the same temperature, as a result some heat being released, right, and this heat being utilized to enhance this temperature of the product to adiabatic, right. If you look at actually, is it happening? No, just for the simplicity to make you understand what is happening, I have drawn that actual process is going in this way. That means, reactant is going to the product with having a temperature, adiabatic temperature, higher temperature, right. So, you can think of the heat being released and it is being, the product temperature is being raised due to sensible enthalpy rise, because it is the adiabatic process. Even though it is non-adiabatic, still it will be increasing, but you will get a temperature which is lower than the adiabatic temperature. In case of some heat might be going, in real system there is no adiabatic temperature as such, okay. It is just a what you call theoretical one. Suppose I want to burn some fuel and oxidizer in a burner, can I get adiabatic temperature? It is quite difficult, because some heat has to be transferred to the atmosphere. Even though you can insulate, but still some amount will be going out. You cannot make insulation 100%, right. As a result, Q cannot be, the heat transfer from the system cannot be really 0, whatever you do. So, that is the reality, and let us now take an example, see that under this ideal condition, ideal mean the sense I do not know the composition, right, but I am assuming certain composition, and composition of what? Composition of product, right. and then estimating the temperature. And keep in mind that this composition will be dependent on the final temperature, that is adiabatic temperature. That means, they will be complementing each other. So, which you do not know. So, what we will do, we will estimate this adiabatic temperature of pentane C5S12 with excess of 25% air, and both this pentane and air enter at the 25 degrees Celsius, and assume the complete combustion. That is again assumption we are doing, and we will do all these assumptions. The change in kinetic, change in potential is 0 and Q is 0, there is no shaft work. So, the first law becomes H P is equal to H R. And if you look at it, this reaction is given, and you can see that it is quite balanced, some amount of oxygen is there, excess oxygen. So, what we will do, we basically products are given like carbon dioxide, water and oxygen, and then these things. So, then we can really find out what is this H P. If you look at it, is having one component, that is 5 HF of CO2, right, that is your heat of formation term, and 6 for the 6 HF water, that is the for water and oxygen and also nitrogen. Beside this, like it is having sensible enthalpy, right. And here what we are doing, we are saying that Cp is not really a, it is remaining constant in this example. What if you look at, this is Cp I dt, which is the function of temperature, right. Okay. And this is 298 to T adiabatic. Of course, there will be an I is equal to 1 to n, right. This term we are now evaluating, and keep in mind that what we are assuming here, actually Cp is not changing over the range of temperature, which is not true. Okay. But for the to make the problem tractable, we are assuming, and then what we will do, we will have to take a average specific heat between the temperature, that is 298 to T adiabatic temperature, which is basically will be a little erroneous, but we can solve the problem making in certain amount of errors. So, that is why we have done. This is a very important assumption, please keep in mind, right. Then of course, HR we know very easily, that is HF, these data are given. So, these data H and then this HF and then these data can be obtained, data are to be obtained from table, right. Which table? This is JNF table, JNF table, or as I told, it is there on the back side of my book, given in the appendix. So, this data information, heat of formation of individual species you can get very easily, we will do that. So, then from first law we know H P is equal to H R, right, and then substitute this H P and H R in that equation, then we will get how to solve that. So, if you look at, if I take this portion and this what you call portion, actually if you look at carbon dioxide and water, this portion is nothing but your heat of reactions, right. This is heat of reaction. So, which is no, and then we will have to substitute these values of Cp, and this must be chosen properly, values of Cp, CO2, water and then oxygen, nitrogen. Otherwise, you will land in getting a temperature which is quite different. So, therefore, judicious has to be it has to be chosen judiciously. But from this heat of reaction we can get this from the substituting these values, and when we will choose these values and we have taken for the Cp, this is the Cp values for the carbon dioxide, and this is for the water, and this is for the what you call O2, and these values is for the Cp values for nitrogen. And when you substitute these values, and if you look at only unknown is T adiabatic, all are known, and this is a 0. So, we will get a temperature which is 1852.3 Kelvin. Sometimes this temperature will not match with whenever you will be using a software to estimate the adiabatic temperature. And in the software, if you look at, it will be taking care of the composition, what will be the composition, final composition, right. So, and mostly we will be doing for this can be used for hand calculation, but it may be very away from the actual data unless otherwise you take these Cp values properly. That is very important, because we are making an assumption of taking average temperature, right. Let us look at how this adiabatic temperature which will be coming, like if I look at the CH4 air, and that is for stoichiometric mixtures, right, only, that is inlet temperature 300, pressure is 0.1, you can get 2200 Kelvin, right. But if I will increase this pressure to what happens, the 2270 Kelvin, it has come from the methane air, which is not really very much higher. That means, the temperature pressure is not having much effect, but however, we will see it is having certain amount of effect. Now, if I will change this to the inlet temperature to the 600 Kelvin, what you find? You will find almost 300 degree kind of thing with respect to this like around 230 Kelvin difference is there, right. Generally, people roughly say that you add the inlet temperature to the adiabatic temperature corresponding to the 298 or 300 Kelvin. So, you will get that, I mean that is roughly. And if instead of air, if I use oxygen, what I get? I get something 3030 Kelvin as compared to the 2200. That means, around 830 difference we get. And if I look at propane, you get 2278 Kelvin. If you look at most of the hydrocarbons, of course, this is the stoichiometric mixture, right, and will be not varying, it will be hovering around 2200 Kelvin, right. You should keep in mind roughly, I mean 2200 to 2300 Kelvin, in that range most of the hydrocarbon air adiabatic temperature. Whereas, if I go for hydrogen, it is having 2390 Kelvins, and of course, hydrogen oxygen will again go to the 3000 order, and CO air is having 2400. This is quite interesting, like how come it is having a higher temperature as compared to the hydrocarbon, particularly CO air, which is quite interesting. Still people have to resolve that, and keep in mind that like you may get a this kind of why it is happening, interesting thing. So, what you can learn from here, that means adiabatic temperature is dependent on pressure, it is dependent on the inlet temperature, and also it is dependent on the type of oxidizer or the fuel you are using, except the hydrocarbon air, which will be having almost to in the range of 2000 to 2300 Kelvin. Okay. So, let us look at how this is. That means, it will be depending on the inlet temperature, inlet pressure, and also it will be depending on the fuel air ratio or the equivalence ratio. Let us look at how it is really varying. I have taken an example of methane air system with 300 Kelvin. If you look at adiabatic temperature is plotted with respect to equivalence ratio, right. If you look at what you are observing that temperature is increasing from the lean limit, like lean mixture, this is the lean mixture, right. This is the rich mixture, right, and this is of course the equivalence ratio 1, that is stoichiometric, right. This is your stoichiometric mixture, this one, right, and it is increasing, having a peak values over here, and again it is decreasing, right. That means, it is increasing from the very lean mixture, and it goes up, and then again peak value, and this peak value for a hydrocarbon occurs around phi is equal to 1.05 and it decreases. Keep in mind the slope is very steeper in the lean side and on it is little less steeper as compared to the lean side on the in the case of rich mixtures, right. Why it is so? It is a matter to be pondered about it. And similarly, when you increase this inlet temperature to 600 Kelvin, that is the red line which indicate the similar feature. And most of the hydrocarbon mixtures will be having similar feature. So, also the other hydrogen, air and all this thing. So, let us now look at how it is varying with initial temperature. And if you look at, I have taken a Stokes 3 equivalence ratios methane air system. One is of course, the 1, this is the phi is equal to 1, and if you look at with inlet temperature, the adiabatic temperature just increases and phi is equal to 1.5, this is phi is equal to 1.5 and this is phi is equal to 0.5. Of course, all are having similar features, right, like it is and keep in mind that as you go on, we cannot really go beyond the 3000 Kelvin, because the dissociation will be occurring. If dissociation occur, then the temperature will be brought back to the around that number of 3000 or odd numbers. So, let us look at how this pressure affects that adiabatic temperature. If you look at, it is at the lower pressure, it is increasing steeply, after that it is asymptotically increases, and keep in mind that beyond 0.8 like kind of temperature, that is the temperature increase will not be very much due to the no change in chemical composition, particularly at high pressure, right. So, therefore, I am like it is high pressure, it is not really changing much, but in the low pressure region the effect is very significant in the temperature. So, now what we have discussed till now about adiabatic temperature is that we assume the compositions, but whether we know this composition or not, right. For example, like if I take the let us say hydrogen reacting with oxygen, and we can always say it is going to the water. For example, if I take a container and I put some hydrogen and oxygen, right, with a particular proportion, what you call ratio, right, then what will happen? Can really reaction occur? For example, if I take this room and fill with hydrogen and oxygen or air, can really reaction takes place? It will go to the product? Certainly no, you need to ignite it. Of course, if you even give the initial ignition energy, whether all the hydrogen or the oxygen will be going to the water, you really, I mean whether it is possible or not, that will be dependent on what? In real situation it may not, right. But of course, if the pressure is constant, so also the temperature is constant, right, then composition, chemical composition will not change. But however, how will determine what will be the composition of the some reaction will be taking place. Keep in mind that whatever the reaction I have written here need not to be there in real situation. There might be several reaction steps which will be there, right, which will be involved, and this is just a global reaction or a representative reaction, overall reactions whatever it will be occurring, right. Now, how to go about it? We are interested to know composition, because our objective is to determine the adiabatic temperature. Unless I know the composition, I cannot estimate adiabatic temperature. Unless I know the adiabatic temperature, I cannot estimate the composition, right, product, that means composition of the product. So, how to go about it? What we will have to do? We will have to basically find out the state of equilibrium, how far it is reach equilibrium, right. Now, question arises how to find out the state of equilibrium, because if it has gone some hydrogen is reacting and oxygen is going and it is going in the forward direction, right. to water, and water can also decompose into the oxygen or to the water hydrogen. Now, what else? If I consider only this reaction, of course, in real situation there might be several kind of reaction will be occurring, but I will just consider this reaction itself for the simplicity. Now, how we will find out whether equilibrium reach, because if it equilibrium reach, that means forward reaction will be same as that of the equilibrium reaction, and that of the forward reaction is will be same as that of the backward reactions, right, rate, right. But how we will go? How we will say that it has reached equilibrium, whether it is possible or not? For that we need to invoke the second law of thermodynamics, right, because that will give us the direction of the reactants, whether it will be what is the percentage of reaction is converted, or it is the how much will be the product. For that we need to invoke second law of thermodynamics, which states that change in entropy of the system must be greater than equal to the del q by T, right. This we have already studied, and for an adiabatic system what it would be, right, it will be basically will be 0, change in entropy will be 0. That means, if it is greater than equal to 0, then I can system can proceed, otherwise no. For example, like you want to see that whether chemical reaction proceed in what you call in particular direction or not, then there will be increase in entropy or it will be equal to the 0, right. So, let us look at how this process takes place. For example, if I say that this is 100% reactant, right, and this will be 100% product. For example, I am taking a hydrogen reacting with oxygen going to the product. So, but the reaction will proceed as long as the change in entropy is greater than 0, right. But it will go till it reaches a maximum point where the change in entropy will be 0, and as this portion will be violating second law of thermodynamics, therefore, it cannot really take place. That means, it will reach the equilibrium composition when the change in entropy will be 0, and that is valid only for what? Only for an adiabatic system, right. But we know that in our system there will be several places where need not to be adiabatic, right. So, then we need to think about a concept or a which is known as Gibbs free energy. We know by definition G is equal to H minus T s, right, and H is the enthalpy, T is the temperature, S is the entropy. So, if I just differentiate, what I will do, I will get this d G is equal to d H minus T d s, right, and minus S d T, right. And we know like the temperature we need to remain constant. So, I can make this as a 0 like whenever this equilibrium is talking about. So, H then by definition H is equal to U plus P v, and if I just differentiate this expression H is equal to U plus P v, what I will get d H is equal to d U plus P d V and plus V d P, and keep in mind that we are assuming that pressure during equilibrium is not changing. So, this is basically 0. So, if I just substitute these values, because at the constant pressure and temperature, these values over here, what I will get? That means, d H is basically U plus P d V, then I will put over in this, and what I will get? d Z is equal to d U plus P d V minus T d S. And if you look at what is this term, from the first law we know that d Q is equal to d U plus P d V. So, this term is nothing but d Q, right. So, I can say that the d G is basically d Q minus T d S. So, if I go to the according to the second law of thermodynamics, right, I can write down T d S is greater than equal to d Q, or I can write down d Q minus T d S less than equal to 0, right, because I am just saying this is greater than that. That means, d Q minus T d S will be less than equal to 0. And what is that? This we have already seen dq minus T is, that is nothing but dz is less than equal to 0. So, what we will have to do in case of non-adiabatic systems, we can think of dz will be less than equal to 0, that as a which is also a function of temperature, pressure and number of moles, but we will be assuming that temperature and pressure is not real changing at that moment. So, the reaction will attain its chemical equilibrium when Gibbs function attains a minimum value, that is change in Gibbs function will be equal to 0. Let us look at pictorially. That is this is 100% reactants and 100% product. The process going on in this process till it reaches this point where the equilibrium composition level. That means, we need to estimate equilibrium composition dz, right. And here this is not possible in this portion. That means, because it will be violating the second law of thermodynamics, and therefore, we can't really get 100% product in real situations, right. And we will see that this concept we will be using in the next class, and see that how we can get the composition. Then of course, after that I will be moving into the chemical kinetics, and we will also learn how this composition can be clubbed to estimate the adiabatic temperature, that means in a very iterative way, that we will see in the next class.